This is a second part of a video for section 5.3.2. So you've already read about and learned about the fundamental theorem of calculus as an introduction, and you've already learned how to do the fundamental theorem of calculus part 2 logistically. So we're just going to look at a few other variations of questions. And I want to start actually by looking at some of the properties of definite integrals. Remember, a definite integral is an integral where you are evaluating with limits of integration. So you have a lower limit and an upper limit. You are finding a numeric value that represents the area under a curve. So this first property says that if you are integrating from a number to a number, so from 2 to 2, well, obviously, if you're finding the area of something from 2 to 2, there is no area because there's no width to the interval that you're looking at, which is why the answer is 0. For the one right below that, if you are evaluating the area under a curve from B to A, it is the same as the area from A to B, except your sign will change. And a good example of that is, let's say I was going from 2 to 3. And I found this area in here. Well, if I instead reversed it and tried to find the area from 3 to 2, now I'm going backwards. The area is the same, it's just that the area will now be referenced as a negative value instead. So if you ever need to switch your limits of integration, you can do so by including a negative out in front of your integral. Right below that, we have the integral from A to B plus the integral from B to C equals the integral from A to C. So a nice example of that is, let's say we had a curve, and this is 2, this is 3, this is 5. So if we were to find the area from 2 to 3, I'll call that area 1, and then find the area from 3 to 5, I'll call that area 2. That would be the same as finding the area from 2 to 5. So when they talk about A to B, that would be like 2 to 3. B to C would be 3 to 5. That is equivalent to the area from A to C, so that would be like from 2 to 5. So it's just combining areas together when they have a common limit of integration. Right below that, we have the integration, or the integral of a sum of functions or a difference of functions is equivalent to the integral of the first function plus or minus the integral of the second function. So if you ever needed to split out a function, you can do that. You can also reverse the process, and you can combine two separate functions as long as they have the same limits of integration. And then we have one more over here that we're going to use a lot, and that is when you see a constant number in front of your f of x, you can pull that constant number out as a multiplier way out in the front. So for example, if I had a function like this, and my value was 8 times ln of x, something like that, if you wanted to pull your 8 out to the front, you could. And obviously we'd have a dx on there. Okay, so what we'd like to do is just look at a few more applications of the fundamental theorem of calculus. So they're asking us to find the area between the x-axis, y equals x cubed, from x equals 1 to x equals 2, and then use technology to check your answer. So we're not given the setup for my integral. We're going to set that up. And then we'll take a look at the picture as well. So I'm going to draw the picture first. So we have this function, y equals x cubed. We know what an x cubed function looks like. We're finding the area from x equals 1 to x equals 2. So this is my area right in here that I'm finding. And we're also finding the area bound by the x-axis. So when we set up our integral, our limits are from 1 to 2. And then we're going to use our function x cubed dx. And now we're going to use our part 2 of our fundamental theorem of calculus to evaluate the integral. So we're going to start by finding the antiderivative of x cubed. So we're going to reverse our power rule. So x to the 4th over 4 And remember, you can include the plus c on there if you want, but whenever we have a definite integral, the plus c's cancel out anyways. And we're going to be evaluating this from 1 to 2. So I'm going to substitute 2 in. So we would have 2 to the 4th over 4. I'm going to substitute 1 in. So 1 to the 4th over 4. So that would be 16 over 4 minus 1 over 4, which is 15 over 4. So the area under that curve is 15/4. Now we're going to go ahead and test this on the calculator. So first thing we're going to do is graph our function. Actually, we don't really need to graph it in order to find the integral. We're going to go to our home screen to do this. Whoops. All right, so we have this lovely secret menu when you hit your alpha key right here. It opens up my secret menu. I'm going to choose alpha window. And if you jump down to function number 4, that is function integral. And so it's going to set up that integral notation for us. So we're going to insert our lower boundary, our lower limit of integration of 1, our upper limit of 2. Our function is x cubed dx. And we got 3.75, and if you're not sure if that's the same thing, go ahead and divide out your answer, and sure enough, we got 3.75. So now you know how to find this algebraically. You also know how to find it on the calculator. If you are an IB student, if you ever have an integral problem and the directions say write down, that means you don't have to show any supporting work. I would go straight to my calculator to get your numeric answer. Okay, take a look at number 8. Use the fundamental theorem of calculus to find the area between the x-axis, y equals e to the x, from 0 to 1.5. All right, we're going to do the same thing here. We're going to sketch this. So e to the x is an exponential function. And we are going to be summing this up from x equals 0 to x equals 1.5. So this is a visual representation of what we're finding. Now let's go ahead and set up our integral. So our limits of integration are from 0 to 1.5, and our function is e to the x dx. So we'll use our fundamental theorem of calculus part 2. Let's find my antiderivative of e to the x, which we know is e to the x, and I'm going to evaluate that from 0 to 1.5. So I'm going to substitute 1.5 in here, and then I'm going to subtract what I get when I substitute 0 in here. And e to the 0 is equivalent to 1, so you could write e to the 1.5 minus 1, and that would be an exact answer. If they wanted an approximation, we would have e, remember your e key is right above your ln key right here. So you'd hit the second option and then your e. So then we would have e to the 1.5 minus 1, which gives us approximately 3.48. And if we're going to check that on the calculator, we would hit my alpha window. We would go down to my function integral. Our limits are from 0 to 1.5. Our function is e to the x dx. And sure enough, we get 3.48. All right. Let's take a look at example number 9. So example number 9 says we're going to use technology to find the area of the shaded region. Then check your answer using what you learned in geometry. Okay, so we're going to start with technology here. So we're going to set up our integral, and if you look at your shaded region, the limits go from 0 to 3, and the function is given to us. So it is the square root of 9 minus x squared dx. And this is not something I would expect you to be able to find the antiderivative of. That's not a reverse of a power rule. So that's why we are using technology to solve this. So we're going to go straight to our calculator. We're going to go to alpha window, and we're going to choose option number 4. We're going to use the limits from 0 to 3 of the square root of 9 minus x squared dx. Ooh, it's really thinking on that one. All right, so we got 7.07 for the area of the shaded region. So this problem is asking us to check our answer based on what we learned in geometry. So this is actually a quarter of a circle. So if we just go back to our basic geometry formulas, the area of a circle is pi r squared, and this has a radius of 3. So we would have pi times 3 squared, or 9 pi for the full circle, but we're only looking at a quarter of that. So we really only want 1/4 of 9 pi, or 9 pi over 4. So let's take a look and see if 9 pi over 4 is equivalent to what we found. And sure enough, it is. It confirms that we got the same exact answer, 7.07. So that is the end of our definite integral section. What we have coming up next is part 1 of our fundamental theorem of calculus, but that will be a separate video. Thank you so much for listening. Good luck to you.